Hello, this is Math 2270 coming to you from the College of DuPage during the summer of 2020, and this is the first continuation of the lecture entitled Solving Systems of First Order Differential Equations. Okay, so we're going to continue looking at solutions to this kind of matrix equation, and we know that we're going to be looking at solutions that are of this form, where this is the eigenvalues and that is the associated eigenvector. But this time we're going to be looking at problems where the eigenvalues of the matrix A are complex. They have a non-zero imaginary part. And this is going to seem similar to what we did before, but maybe a little more complicated. So let's dive in just with an example, not so much theory talk. I'm going to ask you to solve this IVP. Now, we're starting with real numbers here, so we want to end up with real numbers. And so take this as far as you can, and we'll go from there. You know what to do. Let's see how you did. Okay, so first thing you do is you're going to have to find the eigenvalues, and you find them to be plus or minus 3 square root of 3 times I. That I is not underneath the radical. So what we're going to do is we're going to take these values, this value, and substitute it into the equation. And so when we do that, we're going to get this, and to find the eigenvectors, we're going to solve this equation. So when we multiply those things, we get this, and that tells us that a to 2 is equal to minus 1/3 times 1 minus square root of 3 times I, and that is a to 1. So that means that when we go up here and do our eigenvector, we're going to get that this is 3 in the top, and then it is going to be minus 1 plus 3 square root of 3 I in the bottom. Now, we know from the theory that at least I shared with you that if one of these is an eigenvalue, then its complex conjugate is, and the eigenvectors also are complex conjugates of one with another. And so the second eigenvector is going to be this one. Now, we're not even going to need that one, though, because they're just conjugates of each other. And so we're just going to have everything we need from the first one. And that means that this is what we would write. Now, this is going to be e to the square root of e to the 3 square root of 3i times t, and this is the eigenvector. But now what we're going to do is we're going to say that e to the it is going to be equal to this. So I'm using Euler's formula, multiplying it times this. So I multiply through and get this. I'm distributing this vector through there, and I'll get this as the top component and this as the bottom component. And now what we have to do is do some algebra here, and we need to find the real parts, and some of this is real, and the imaginary parts, and some of it is imaginary. So we have to do quite a bit of algebra to simplify that, and you should make sure that you can do this algebra. But when we do that, we will now break it into, this is the real vector plus I times another real vector, and just to abbreviate things, I'm going to call this u of t plus I v of t. Now, it can be shown, and what you would do here is you would find the Wronskian of this. Again, no derivatives are required. You're just going to take the, these are going to be columns, and you're going to show that that Wronskian is not equal to 0, and you could do that. But these u and v found this way are two linearly independent solutions to the system of differential equations. So that means that actually this part also is real. There's the imaginary part, and there's this. So those are both real. They must both be real solutions. So what we're going to say is that the general solution to the system is going to be C1 u of t plus C2 v of t, where u and v are vectors. And so we're going to know that this is what we have. That was the real part, and that was the imaginary part. And now we're going to apply our initial conditions that were way back at the beginning of the problem to this. And we'll get two equations and two unknowns, and we can solve for what are these coefficients. And so C1 is 2/3, and C2 is minus 10 over 3 root 3. And so the actual solution then is given this way. It is the sum of those two with the coefficients as indicated. Neat, huh? Let's go on and do another example, and I'm going to ask you to do this one. Solve this initial value problem given here. And there's the initial condition. You know what to do. Let's see how you did. Well, you're going to proceed much as we did before. You're going to find the eigenvalues. This time they're going to be 2 plus or minus 8i. We'll take the first one, 2 plus 8i. Substitute that value in for lambda here, and this gives us equations that will give us the eigenvector. And we work through that, and we'll get that the eigenvector is 1 plus 8i over 5. And again, we don't have to worry about the other part because that's just going to be the complex conjugate of this. So what I'm going to do then is I'm going to write that the solution that corresponds to this is going to be, and this is e to the lambda t times this vector, and I'm going to factor out the e to the 2t, and so here I have by Euler's formula 8i times t, and so here is the exponential that's a real e to the 2t times Euler's formula for that part times this. Now there's a lot of calculation involved here, and you got to be aware of I times I is -1, and so on and so forth. But this then will become this after I do the algebra and I separate the I. So I have e to the 2t times this thing, plus this is I times e to the 2t times this thing. I think about this as being u plus v. So the general solution to this system is given by C1 e to the 2t times this vector plus C2 e to the 2t times this vector. But we're going to use our initial condition from up here to get two equations and two unknowns, which we can solve. And so the actual and final solution is x of t is this. And notice that there are the exponentials on the outside, and we have these trig functions inside those parentheses, and we have the coefficients. So that is the solution. To be continued in 37.2.